Okay, so kicking off the first round of talks is Shiwei Ten. Shiwei was a postdoc of Stephen's from 2008 until 2009. He's now on the faculty in Singapore, so thank you for traveling as far as you have.
Thank you so much.
Over to you.
Yeah.
So it is a great pleasure to be here, and thank you so much, Stephen, and the organizers for inviting such an excellent workshop. So I will be sharing with you large-scale optimization of convex-concave games in networks, and we'll see a few applications. I think the very first application is one that is very familiar to us. So the problem statement is related to technologies such as digital contact tracing, which perhaps will be useful for addressing the next pandemic, which we do not know when it will come. But it also finds applications, for example, in computer viruses in networks, or for example, information disseminations, and information could potentially be created by human or AI. So we want to know which node or which vertex in the graph is the most influential. So that is the key problem statement. So in the next few slides, I'm going to sort of motivate you this problem and also introduce a few other problems that are related to so-called convex-concave games. Like what you see here, it's a small network. What you can see is that there are white and black shaded person. For example, this might be an online social network. And they are identified, for example, these 6 persons identified as potentially having some rumors or viruses. You want to ask, who is the culprit, or who is the rumor monger? Okay. So we want to model such a problem using graph. For example, the human could potentially be just vertices, and the connections between human, they could be social contact graph, social contact network. They can be modeled by edges on this graph. And if these are, for example, computers, right, in the internet network, then these vertices could potentially be the computers, and the links between these computers could be the the bandwidth and the edges that connect those computing devices. So roughly speaking, our problem boils down to saying that, well, if we see a subgraph within a bigger graph, can we sort of say anything about spreading patterns on such kind of networks? And what kind of problems should we address, right, with such kind of data coming from graph structured network? For example, in the COVID-19 pandemic, we may ask, where is patient 0, right? Once digital contact tracing has identified, for example, the infected persons, right? Who was patient 0? So roughly speaking, this problem has been looked at for around 10 years or more, slightly more. So people look at different diffusion processes, for example, susceptible infectious spreading model. And there are also other kinds of very complex spreading models. But we will, for this talk, just confine on so-called SI, susceptible infectious spreading model. We also make some assumptions like each person or each vertex is equally likely to be the source. And so we want to know, once we have the data, can we answer the question, who is the culprit? Let's take a look at how spreading might work using this simple spreading model. For example, say suppose I know at time 0, right, the one in red is patient 0. And this person has 5 neighbors, and with certain probability, right, he or she can spread to the next person. So at time 2, for example, that person up there has been infected. So what you see is that, well, the probabilities change, right, from time to time. And another thing we can observe is that the so-called boundary of this infection graph, which is connected subgraph, okay, grows over time, right? For example, at time t equals 3, right? For example, this guy now is infected. So we have 3 people being infected. The probabilities are being updated at the same time. And this is time equals 4, right? And then after that, we have time equals 5. And eventually, at time equals 6, well, we have 6 people being infected. And so the probabilities change over time. Okay? And this is with the hindsight that we know who is patient 0, right? Namely, that guy in red. Okay.
Could I ask a quick question?
Yes.
So you're assuming only one gets infected at each round?
I assume, yeah, that's a good question because for the SI model, we might say, the time from one infection to the next is exponentially distributed, right? So then you don't get two colliding, right, at that time instance. So that's a good question. So you can think of it as saying that I've somewhat applied the exponential time distribution over time to discretize the time. And say suppose if I were to know this spreading order, then I could compute the probabilities based on what you have seen just now. And that is my so-called spreading order probability, the probability of seeing this piece of data. But this is knowing how these orders came about. What if I do not have that hindsight, but I only know, who's infected and who's connected to whom, right? Then can we sort of solve the same problem, finding patient zero? For example, if I just have this original piece of data, right? The same piece of data, and then I ask, oh, who is patient zero? Who is the most likely to be patient zero? So I might make an error. So I like to minimize the error. So to do that, I may want to, say, formulate an optimization problem, so like maximizing the likelihood of seeing that piece of data, condition on that piece of data, and ask, well, of all those vertices, which could be very large, right, on the infected subgraph, and they are namely a connected subgraph of the underlying, right, graph. What is the, should I say, which one is a patient zero? Okay, that maximize this objective function. So we have actually published a research monograph last year. So this year, we look at decomposition, which is also a very key idea used by Stephen in his earlier work on TCP. Namely, this problem is somewhat intractable. It's combinatorics, optimization problem. So can we sort of devise some nice heuristics, right, to approach this problem? For example, for the degree regulatory network, we know how to solve it in polynomial time. But when the graph, which is in practice the case, right, is irregular, then solving this problem becomes very hard. Okay? So you can see that really digital contact tracing will be beneficial, right? Technologies will be beneficial if we can solve this problem. Yes.
Is the graph time changing, or the contact graph is stable or steady, or be changing over time?
Yeah, that's a good question. So for example, in this, if I formulate this as an optimization problem, the G is a given, assuming it is given, so it doesn't change. And this G sub n depends on the digital contact tracing technologies. How fast it can perhaps meet the speed of spreading, for example, then I may only have certain piece of data, G sub n. So out of these n vertices, of course, it can grow very quickly. For example, in the early days of COVID-19, spreading rate was, the reproduction number was very high. Then this n can go very high, very big, very quickly, right? So we, again, here we want to know, how to address this problem. And turns out that actually, as I mentioned, there were special cases being identified, for example, degree regulatory. And we are using these developments to build sort of like more efficient heuristics to address those harder to solve problems, for example, irregular graph, okay, or general graph. And this depends on the so-called infection graph spreading pattern. For example, in this contagion graph, I might want to solve, for example, this is not degree regular, then I might want to decompose it into manageable or simple structures. And these simple structures are what we call star. In fact, one of our keynote speakers, Srikant, he did something on that earlier on. So star network, they have very nice structure. So here is the idea. This is, again, a heuristic. We want to sort of approximate the underlying, the G sub n, the infection graph, using star-like graph approximation. It turns out that we saw that this is very new, even in graph theory. There were earlier work done on this, but there were not so much applications along that line. So why is star network interesting? For example, in this graph, what you see is that, say, suppose this on the left, again, a very small infection graph, but one which has cycle. So with cycle, it's not degree, this is degree regular graph, but it is not a degree regular tree. So therefore, in principle, it cannot be solved in polynomial time. But turns out that if we use the heuristics, there is a BFS, breadth first search, And again, depending on how you construct that breadth search, you may get different topology. Then you want to sort of expand this or decompose this into a star-like graph. Now, a star-like graph to network people is very intuitive. It is like saying that, well, say suppose I'm the source, and I have a piece of data to send. And all the links, right, connecting all those vertices, they are like exponential service time, right? So they are as if they are like MM1. So it's as if I have like a line of MM1Q. So given that kind of network topology, I may want to ask, well, which vertex should I put my data so that it gets sent and reach out to those leaves or those boundaries that I want to see. And that vertex is hopefully the one that can maximizes sort of or minimize the latency time, okay? Maximize the time, maximize the efficiency of us sending the same piece of data. So here you see that we plot this likelihood function, right, using these heuristics for this simple star-like network. Now that's one approach, decomposition. Another approach is to say, well, if I were to compute probability, or like condition probability, one thing I could leverage on is so-called spectral ranking, or an algorithm that we call a Markov chain, right, which simulates that spreading and tries to solve for that, solve for the optimal solution of that problem somehow. Now, it turns out that for example, degree regular tree network, we could build such a transition probability matrix. This was shown by Shah at MIT. So what we wanted to really develop is to build on this. You can think of this as a Monte Carlo kind of algorithm, one in which we would then leverage, say, PageRank algorithm. Now recall that if I have a very general graph, there are different ways to decompose that into different breadth search tree, right? There may be one that's the correct one, okay? But if we do not know, then we just use all of them and try to combine them and do some averaging in order to sort of try to understand which kind of vertices in this network is the more important one, more influential, so to speak. Now, using our heuristics, we could actually, or PageRank heuristics, we could demonstrate that the performance is much better, right, than prior state-of-the-art, which was just based on one particular breadth search heuristic and using this notion called the rumor centrality. Okay. Now, once we have this PageRank algorithm, the next thing is to say that can we solve this PageRank fast? PageRank has been studied, well studied. Now, but what actually intrigued me is to see PageRank as a convex-concave game. In the last 10 to 15 years, there were attempts on doing this, namely from those optimization theoretic researchers, the Russians, right, Polyak, Boyd, and quite a few from Polyak's students in the past. So here is one sort of results to characterize the spectral characteristics of PageRank. Namely, it can be written as a sort of like a minimax or maximin problems. And there are physical interpretations related to this maximum problem, minimax problem. For example, the optimal solution, right? For example, related to that matrix, I want to find for example, looking at this thing, I want to find, and this is non-convex, I want to find the probability P, which corresponds to the PageRank solution, right? The right eigenvector corresponding to this non-negative matrix. Turns out that if I solve this max problem, this lambda over here corresponds to finding the right and left eigenvectors and try to make the Kronecker products. And it has a physical meaning. It's saying that, well, this lambda over here is the probability that if I start at this vertex and I do a random walk, the probability that I will return back to the same vertex. So this is also somewhat intriguing because from Perron-Fubini's theory, right, the right and the left eigenvectors, they have very nice intricate relationship. Now here's another sort of convex-concave game, right? So just now we saw who should we infect, right? Who should we spread? You know, who should we spread our virus or our information to, right? So as to maximize the spread, okay? Now, then there's a sort of counter problem, which is who to protect as well. So think of this as like a two-player game theoretic problems. And very interestingly, this problem has been looked at by two groups of people, one Fang Chong, Cohen, and Ronald Graham, right? In the past, they call this a pursuit evasion games on graph. For example, say suppose I have two players, red and blue, and I'm given a graph, right? So the red player says, hey, I want to choose a vertex from this graph, and the blue will play next. And red will pay blue, right, an amount equal to the distance. So when I say distance, it means the number of hops in this graph. And there happens to be another work, right, by Boyd and Ghosh in 2003. They look at minimax and convex-concave game, and they use the same kind of problem formulation and assumption. And it turns out that for this problem formulation, you could look at a payoff matrix which is square and non-negative. And so then you can really sort of like try to think if I can solve an optimization problem over this graph. So here you see that what we have is like an entropic regularized minimax game or bimatrix games. And here that A is like a square non-negative matrix. We could leverage results in Perrin-Frobenius theory and also optimization theory to solve this problem. But taking notes that there are a few key takeaways that these kind of problems are usually very tricky. For example, we saw that there's a counterintuitive behavior in these game theoretic problems. So here we are leveraging past results like Perrin-Frobenius theory that we have done with Stephen. And for example, Perrin-Frobenius theory was very instrumental in solving this zero duality gap problems, right, in optimal power flow. Okay. Now, to conclude with a lighter note, okay, all these network optimizations have a lot to do with the science of juggling and AI. For example, like this guy on the left, that's Claude Shannon. He initiated the science of juggling, and he built robotic machines to do juggling. And this gentleman here in the middle is Ronald Graham, so he's juggling. And it turns out that juggling has a lot to do with Caltech as well, because Ronald Graham, he studied the mathematics of juggling, which is called side swap. Turns out to be invented by two jugglers who were students at Caltech. Okay. For example, all this juggling can be modeled by Markov chain. And this can be interesting because new juggling patterns can be discovered in the process of, for example, let me demonstrate what Claude Shannon and Feynman, they are doing so-called basic cascade, like 3 balls, right? So this is the basic cascade. Yeah. Now, the basic cascade has one Markov chain, but the same 3 balls, right? I could have, this is called the 4-4-1 using the side swap, okay? A different kind of, oops. And of course, if you add one more ball, the Markov chains get bigger and more challenging, like what Ronald Graham is doing. This is called a fountain. Oh, that's harder. Thank you. Yeah. So to conclude, I'd like to extend my birthday wishes, special birthday wishes to Stephen. Stephen is a very inspiring teacher, and his dedication and passion has made significant impact to all of us. And actually, I have prepared quite a few gifts for Stephen, and one of them is a juggling ball. Because in my eyes, Stephen is an excellent juggler, a master juggler who juggles both research, entrepreneurship. He co-founded FastSoft and PowerFlex, as well as mentorship. So thank you very much, Stephen, for your contribution and guidance.
I think we have time for one question while the next speaker sets up, and also for any speakers coming up, if you have any other party tricks, I will absolutely allow it to run on.
And of course, I'll be delighted. They're small kids, so I'm happy to teach some juggling.